Hi, in this lecture we are going to talk about the theoretical background for bubble sort. So, let's get started. Basically, what is this bubble sort? It repeatedly steps through the list to be sorted, compares each pair of adjacent items and swaps them if they are in the wrong order. It is too slow and impractical for most problems, even when compared to insertion sort, for example. This sorting algorithm has a worst case and average case running time complexity ortho n squared. So bubble sort is a typical quadratic running time algorithm. And basically we can do better. We can achieve ortho n log n running time with the help of comparison based algorithms. So that's why usually we don't use bubble sort at all. Bubble sort is not a practical sorting algorithm. It won't be efficient in the case of a reverse ordered collection. But on the other hand, it is a stable sorting algorithm and it is in place, so doesn't need any additional memory. Okay, so we have been talking about that bubble sort is not an efficient algorithm, but in computer graphics, it is popular for its capability to detect a very small error, like a swap of just two elements, for example, in almost sorted arrays and fix it with just linear complexity, ortho n. Or for example, it is used in a polygon filling algorithm where bounding lines are sorted by their x coordinates at a specific scanline, and with incrementing y, their order change only at intersections of two lines. So as you can see, it is not a practical algorithm, it is not the most efficient one, but on the other hand, it can have some applications as well. Okay, so what about the source code? For example, we have a one-dimensional array -3, 4, 88, 1 and 3. We iterate through all the items in the array. Of course, we have to consider every single item, of course. Okay, and on every iteration, we keep considering fewer and fewer items because on every iteration, we consider one more item to be sorted. Okay, and if necessary, we swap the two items, because array at the j index is greater than the array at the j+1 index. It means that it's not going to be in an ascending order, so we have to swap the two items. Okay, so let's see. We start at the beginning, of course, and we keep comparing the two adjacent items, -3 and 4, because -3 is smaller than 4, they are in the right order. Okay, what about the next one? We compare 4 and 88. Okay, 88 is greater than 4, so again, they are in the right position. As you can see, we just have to swap them if the array j is greater than the array j+1. So this is greater, this is the j index, and this is the j+1 on the right. Okay, again, we don't have to swap. Then what about 88 and 1? Of course, we have to make some swap operation and we have to change their positions. What about the next one, 88 and 3? Of course, we have to swap them, and after the swap operation, we know for certain that this number is the greatest one in the whole array. So that's why we have to decrement the range with the I index, because on every iteration we bubble up the largest item. So in the second iteration, we know that one item is at its right position. On the third iteration, we know that two items are in their right positions. On the fourth iteration, we know that 3 items and so on. So that's why we have to decrement the range basically on every outer iteration. Okay, of course, then we start again. -3 and 4, they are in good position. What about 4 and 1? Of course, we have to swap them. What about 4 and 3? Basically, what's very important to see that we have to compare adjacent items. We don't compare -3 and 4, -3 and 3. We compare adjacent items. They are not in the right position, so we swap them. And again, 4 is in its right position because 4 is greater than every other item. Okay, we don't talk about 88 because we have already considered it, but 4 is the second largest item in the array. And we start again. -3 and 1. -3 is smaller, so they are in the right order. What about 1 and 3? Again, they are in the right order, so 3 is the third largest item in the array. We start again. -3 and 1. They are in the right position, so we don't have to swap them. We consider 1 to be in its final position, and we have a single item left, which is by definition in its right order. So this is how we can implement a bubble sort, and we can end up with the sorted order -3, 1, 3, 4 and 88. In the next lecture, we are going to implement it. Thanks for watching.